It is a great pleasure to be here and to have a chance to talk about what we do. It's been a great pleasure to be able to be in the community of scientists that just spent 2 very productive days together, trading ideas and criticisms and suggestions at each other. It was a very productive meeting that we've just come from. And earlier this morning, I actually presented my work to that group and had a PowerPoint deck of about 25, 26 slides, very data intense. And I thought for this group, I would just stand here and tell you what I did without any slides, because the level of technical detail, it goes well beyond what I think the interest in this room is about. But I do need to start with a little biology, otherwise it's just impossible to explain what I do. So let me take you back to what's called the central dogma of molecular biology, which is that DNA, the stuff of our genes, makes RNA, which is the transition point between the genetic code, and that DNA makes RNA, and then the RNA makes protein. And it is the proteins, really, in our cells that give our cells the structure and also allow them to function in a way that is meaningful. And you have to multiply that by all the different cell types and all the different proteins, and eventually you get to functioning cells and functioning organs and functioning people. So that's the simple explanation. But what we've learned over the last, 50 years is that it's actually a little bit more complicated than that. So DNA makes RNA makes protein, but the DNA doesn't sit naked, at least in eukaryotic cells, which are the cells in our bodies. They sit wrapped in these proteins called histones. And the histones are there in part to balance the charge and make the DNA more neutral inside the nucleus of the cell. But over time, they've evolved to help regulate that central dogma, how DNA makes RNA makes protein. So in other words, the histones indirectly, by wrapping the DNA, influence the structure and function of cells. And the only analogy I've been able to come up with recently is the analogy of an overcoat. The way in which the histones regulate the DNA is sort of like this jacket that I'm wearing. So when it's loose, I can reach in my shirt pocket and pull out the pen that I write all my good ideas about the brain down with. And I can reach into my other pocket, pull out the apple in case I get hungry. But if I tighten my overcoat, I can't get at my brain ideas anymore. They're bound up inside. But fortunately, I'm not going to die because I can still eat. And that's essentially what the histones are doing. They're loosening or tightening around the DNA. And so they add a level of complexity to that central dogma of molecular biology. Now we can fast forward to about 2 years ago when a very talented postdoc in my laboratory, Jalili, decided that he wanted to work on histones in the context of ATM. And about half the story is the story that was published in April, and the other half has not been published yet. I talked about it this morning, and I'll summarize it here. But basically, ATM is the protein that is, as you know, mutated in the disease we know as ataxia-telangiectasia. But one of the normal functions of the ATM protein seems to be to ensure that the histone jacket around the DNA is loose. Now, there are technical terms for how it does this. The histones can be modified with little chemical decorations. One is called an acetylation, and that acetylation will loosen the coat. And the other is called a methylation. Chemical details don't matter, but the methylation will tighten the coat. ATM acts to loosen the coat in both directions. It increases the acetylation and decreases the methylation. And that brings us to the problem in a group of cells that would be lacking ATM, because now the overcoat around the DNA starts to tighten, and you can't get at the good ideas about the brain, so the cells of the brain do not work as well. Food is still available, so the cells don't die, but there is a distortion in the way in which the cells are able to access information, and it leads to the types of deficiencies, in part, that we see as a function of the ATM deficiency. Now, just to put this all in context, I'd urge you all to remember that this is going on at the same time that ATM is activating all of its other functions. It is very much a DNA damage response protein. So in addition to modulating the coat, it also is a big player, you know, if I break a leg and lose a part of my helix, in having that healed. It's a big, and through that, it's a big player in the health of cells in other ways. So the picture, I want to just be very clear, is complicated. But the histone interaction is an interaction that is really a novel angle, and it offers a fresh and perhaps productive way to get at improving the lot of cells and hence organisms with ATM deficiency. So the question that Jali asked then is that if this is the way things are working, then we ought to, if this is the case, that ATM is serving to loosen the overcoat, then it ought to be the case that if we gave drugs that interfered with taking the deacetylation or the methylation, that we should be able, even in the absence of ATM, to improve some of the functions of the cells. And so we went looking in the literature, and it turns out that we identified 2 drugs that helped to increase the acetylation, and we did a genetic trick that allowed us to decrease the methylation.